The next talk will be a forward quark jet nucleus scattering in a light from Hamiltonian approach given by Meijian. So please go ahead.
Thank you. First, I would like to thank the organizers for giving me this opportunity to talk here. And it's a great pleasure to be here and meeting and discussing with all of you. So I will talk about our work on the quark nucleus scattering in the light from Hamiltonian approach. And this work is in collaboration with Thomas Lappi, Carlos Salgado, and Xinbo Zhao. So the problem we are looking at is the quark scattering of a color field. So the general picture for this kind of process, and there are two interesting aspects with it. So first one is when one considers high energy quark nucleus scattering. So when you really think about an infinitely energetic quark passes through the color glass condensate state of small x gluons inside the high energy nucleus. And so this is the iconal picture. And so the cross section for this process can be calculated analytically through the Wilson line. And then the researcher interests in this area includes the various sub-iconal effects. And the typical correction is you have a finite wave field instead of infinitely short sync wave. And one could also have the gluon emission by doing the going to the next leading order. And there are also correction on the field, and which would change the spin state of the quark jet. And then in another picture, when one think about the jet quenching in the color medium, the probe still in the approximation has infinitely large energy. But this time the field is usually considered as spatially extended. And while the quark going through the medium, it loses energy by gluon emission. And a very interesting study is to investigate and understand the interplay between the coherence time of the gluon emission and the time scale of the scattering centers of the medium. So what we are trying to do here is to make some input from a different perspective, that is to use a non-perturbative approach. And with this, we could relax the infinite energy approximation, meaning that we could let the quark have finite energy instead of infinite energy. And also we explicitly solve the time evolution of the quark state, and therefore we could study the scattering and the gluon emission at the same time. So in the following of my talk, I will first introduce the method we are using, which is a light from Hamiltonian approach for solving time-dependent problems. And then I will talk about in specific how we apply this to study the quark nucleus scattering in the quark plus quark gluon Fock space. And then I will present you some results, both the published one and the preliminary results, and I will summarize in the end. So the method we're using is called the time-dependent basis lifelong quantization. So it combines the lifelong quantization and the Hamiltonian formalism. So being lifelong quantization, meaning that the quantum field is quantized on the equal lifelong time surface, x plus equal to 0, and x plus is defined as x0 plus x3, illustrated in the figure here, the front form. So x plus equal to 0 is the quantization surface. And then correspondingly, the p minus is the lifelong Hamiltonian. And so this is the Hamiltonian formalism. So the state obeys the time evolution equation. So P minus is the Hamiltonian that encodes all the information of the system. And by solving this equation, one could get information of how the state evolve or change through the process of interest. And the treatment we are adopting here to solve this equation is that we divide the time evolution into many time steps, and then each time step can be evaluated numerically with the numerical method, for example, the direct exponentiation or finite different methods. And one could choose the method that is optimal for the specific problem by looking at. Which I will talk about in detail when we go to the specific problem. And then, so this is numerical method. And so when solving this equation numerically, one could also choose a basis representation in the calculation. And the optimal basis has the same symmetries of system, and it is the K to numerical efficiency. So this is the procedure we're using in general. And then moving on to the problem we are looking at, which is the quark nuclear scattering in the quark plus quark gluon space. So this figure, the space-time diagram figure, illustrates the problem we are looking at. So we consider the scattering of a high-energy quark moving in the positive z direction. So the word line of the quark that is indicated by the dashed line, and with also the gluon line indicating there are also gluon component in it. So this is close to the x plus axis. So it scatters on also high energy nucleus that is moving in the negative z direction. So the word line of the nucleus is indicated as the red band here, which is close to the x minus axis. So we describe the nucleus with the MV model and the classical background field. So to describe this problem, we first get the lifelong Hamiltonian that is derived from the QCD Lagrangian with the color background field. So showing as the curly mu here, so that is the background field from the nucleus. And then one could get the lifelong Hamiltonian by doing a Lorentz transformation of the Lagrangian. So the Hamiltonian in this Q plus Qj space contains 3 parts. So P minus Ke is the kinetic energy of the quark system. And then there's 2 interactions. One is with Qj, so that's the gluon emission absorption, which could lead to the transition between the quark and the quark gluon sector. And then, so this way A is the interaction with the background field. And in this table is indicated by the vertical red line. So that the background field interact with each Fock particle, quark and gluon individually. And then about the background field. So here we are treating the background field from the nucleus and the classical gluon field. And so what we are using here is the MV model. So the rho, which are the color charges that generate the field, satisfy the 2-point correlation relation. And the field is solved from this 2-dimensional Poisson equation. And so Mg is introduced as the infrared regulator. And while we are adopting this field into the problem we are looking at, we also discretize the field along the x plus direction. So x plus is the evolution time direction for the quark system, but that is also the longitudinal direction of the nucleus. And along x plus, we divide the field into multiple layers. And then the charges and each layer, they are independent from each other. So this corresponds to the delta function along the x plus direction. And then in solving this problem, the basis we are choosing is that we use the momentum states of the quark and the basis states. And then the quark state would be expanded in the basis space. So the psi x plus is the state and the lifelong time x plus. And this C beta, which is the basis coefficients in this basis space, is the wave function that one could access by solving the evolution equation. So for the Qj space, which is the 2-particle component, the basis state is the direct product of the 2 single particle basis states. And each single particle state carries 5 quantum numbers. So Kx, Ky are the transverse in the transverse dimension, and then K plus is the longitudinal momentum, and so lambda the lifelong elasticity, and then say recalls the color of the state. And in the longitudinal space, x minus, it is treated as a circle of 2L with periodical boundary condition for gluon and anti-periodical boundary condition for the quark. So as a consequence, this means for the P plus, the longitudinal momentum is discretized into the different units for both the quark and the gluon. And then in the transverse coordinate space, it is discretized on a lattice with periodical boundary condition. So here the 2 lattices are the one in the transverse coordinate space, the other is in the transverse momentum space, and they are related through the Fourier and the inverse Fourier transformation. So the total basis size is scaled by n-perp to the fourth. So n-perp is the number of the lenses in the transverse direction. So on this basis, we could solve the time evolution equation explicitly. So we do this in the interaction picture. So as such, the kinetic energy would enter as a phase factor. And then the interaction within each time step has the gluon. So one is the interaction with the background field. So for this, we know since the interaction is local in transverse coordinate space, so it is more efficient to carry out this interaction in the coordinate space by doing matrix exponential. And then we can go back and forth to the momentum space by faster Fourier transform. And then for the interaction that contains the gluon emission and absorption, we use the fourth order Runge-Kutta method in the momentum space. So this calculation is in principle proportional to the n-perp square, but since momentum is conserved, so in practice, the computational cost is O(n). So in total, the computational complexity for each time step is O(n) log n by the faster Fourier transform. So this is the method we are using. And next, I'm going to show you some results we have by doing this simulation. So first, I will discuss the evolution of the quark system. And I will show the effect on both the gluon emission absorption and also the interaction with the background field. So in the first case, we first turn off the background field. So now they are only kinetic energy term and the gluon emission absorption. So this is like the quarks traveling in the vacuum. And to better understand the effect from this process, we use the initial state and just a single quark state with a specific momentum, finite p plus, and a 0 transverse momentum. So the result we're looking at here is the transition of the state. So let's look at the left result first. So this is a case where we also do not have the phase factor, so meaning turning off the kinetic energy term. So this is not physical, but it will be helpful in understanding the result and we get from simulation. So what plotted here is the probability in the function of x plus the evolution time. And there are three legends plotted here. So the solid yellow one is the probability of the quark staying in its initial state, the probability of the initial state, which starts from 1. And then the dashed blue line is for the probability of the different quark. So still in the quark sector, but with different momentum, different color, and so that's the probability of the different quark. And then the dotted red one is the probability for the quark in the QJ sector, summed over all the phase space. And what one gets here is that, so it will never go to the different quark state because there are no background field here. And what one say is the oscillation between the quark sector and the QJ sector. So there's some coherence here. That is because if you look at the Hamiltonian and the matrix element and the matrix in the basis space, without the kinetic energy term, there's only 2 eigenmodes of this problem, and they have the opposite eigenvalues. So what one get is that all the different momentum mode, they would oscillate with the same frequency. So in the end, one gets oscillation between the quark and the quark gluon state. And now going to the physical case, now with the kinetic energy term included, what happened is that different momentum mode, both the quark and the quark gluon, now they have a different kinetic energy term, so they would oscillate with a different frequency. So this would lead to some decoherence. So one no longer say the regular oscillation on the left. So what happened is that the quark component would decrease to some value, And there's still some small oscillation pattern, but it would get suppressed. And then the probability of the quark gluon component would increase. So this indicates the gluon emission and the transition from the quark to the quark gluon component. If you look at this in the transverse momentum space, so on the left, framed in the dashed line, is still for the case that without the phase factor, meaning without the kinetic energy. And what's showing here from the first, from top to bottom, the transverse momentum distribution. Okay, thank you. For the quark in the quark sector, quark in the quark gluon sector, and the gluon in the quark gluon sector. And from left to right, the evolution time x plus is increasing. So you see the initial state is only a single quark, and then as time increase, the QJ component increase, and the value here, the small value here inside each panel is the probability with the plotted that summed over the plotted modes. So since without the phase factor, each momentum mode, they are oscillating with the same frequency. So what one say is just the oscillation of the between the quark and the quark gluon state. But with the phase factor, so going from the right, you can see there's a clear circular pattern here. So this is because now with the phase factor, different momentum mode, they have different P minus, different kinetic energy. So they are oscillating with a different frequency. But together, the full probability, you lose the coherence. So that's what you see here when you look at the transition probability. So this is the effect from the gluon emission absorption with the kinetic energy term. And now we put in the interaction with the background field also. And again, we look at the probability plot and the function of x plus. So the initial state is still a single quark. Now this time, the initial state would decrease, and there's some probability appear in the QG component. But also, since the state is interacting with the background field, the different quark state would also appear. So that is indicated by the dashed blue line here. And going from left to right, we are doing the simulation with the stronger background field. So there you would see the more transition to the different quark component. And then going again, looking at the distribution in the transverse momentum space. So starting with the single quark state. So on the left is using a larger P plus. So this is close to the Eichner limit where you have the what one could think about the fast quark. So the quark goes through the media on a very faster speed compared with what is on the plotted on the right, where one have a smaller P plus, and this is considered and the slow quark. So the difference between the of this and the previous one without background field is that you see the quark here, its distribution in the transfer momentum space gets spread out because it interacts with the background field, and also for the quark and the gluon in the quark gluon sector here. So this is a combined effect with the gluon emission and interaction with the background field. Okay. And now we have seen that through the quark interacting with the nucleus background process, the momentum gets changed. And so such momentum broadening can be characterized as the quenching parameter, the Q hat, which is defined as the change on the P per square over the evolution time in this framework. And firstly, we consider the very simple case if you only have the bare quark. And so the P per square can be evaluated from the wave function of the final state in the quark sector and the expectation value. And then the quenching parameter can be just calculated from this expectation value. And this is actually can also be done analytically in the Eichner limit using the 2-point Wilson-Lie correlator. And what one get is this Q hat is proportional to mu square, which characterizes the strength of the background field or the medium. And then it has a logarithmic dependence on the UV cutoff. And so this UV cutoff on the lattice that we do the simulation it is pi over a perp. So a perp is the lattice spacing in the transverse coordinate space. And this MJ, recall it is the infrared regulator in solving the background field. So this is known analytically, and we also do this numerically. So this may be less exciting, but it's very reassuring in that one could verify this numerically. So this would help verify the simulation we do. So what plotted here is the, okay, thank you, is the Q hat and the function of mu square. So essentially this Q hat and the function of the strength of the background field. So the solid line is the analytical expectation, and those colored markers are all calculated from the simulation. So it agrees with analytical expectation. And then we also check the dependence on the UV cutoff and the infrared regulator. So that is the Q hat divided by Q hat 0. So Q hat 0 is this bare part. So what is basically shown here is the logarithmic dependence on the MJ perp. So there we also have an agreement of our simulated result with the analytical expectation. And then next we go to the case with one gluon. So now in the quark plus quark gluon place, when we still consider the single quark and the initial state, so and x plus equal to 0, meaning the point that the quark meets the medium. So that there you only have a single quark with 0 transverse momentum. And while interacting with the background field, the QJ component would also appear, and also the different quark component, as you say previously. Now, if we want to interpret more on the momentum broadening, here we calculate two quantities. One is just for the bare quark part. So this is the p perp square for just the quark component. And then we also compute the total p perp square, which sums over the p perp square in the quark sector and also the p perp square of the QJ sector. So what is plotted here is the p perp square and the function of x plus. And so for the and we also put a reference line and the analytical expectation. The solid one is the bare quark, and the dashed line is the bare quark plus a bare gluon. So what we see is that for the bare quark one, so our results shown in gray here. So it would increase as the evolution time increase, but it is below the analytical one. So that is because if you look at the probability plot, so the single quark component would decrease. So it starts with 1, but due to gluon emission, it would decrease. So what one gets, if one calculates only the bare quark p perp square, it's below the analytical one. And then what plotted as blue is the total one. So that's the total momentum broadening of the quark in the quark plus quark gluon space. Okay, thank you. And then so we want to understand what is the momentum broadening of a quark state going through the medium. And previously, so here I'm using just a bare quark and the initial state. But if you think about the case where in the physical high energy scattering process, the initial quark, if it is traveling from negative infinity, when it reaches the point and x plus equal to 0, the starting point interacting with the background field, it may already develop a gluon cloud before the interaction. And how we treat this in this framework, so we obtain the draft quark state by solving the eigenvalue equation in the quark plus quark gluon space. So meaning here, the P minus QCD, which is the Liefeld Hamiltonian containing the kinetic energy term and the quark gluon term. So by solving this eigenvalue equation, one gets a spectrum of the draft quark state, and the ground state is considered as the physical quark, and we use this as the initial state to do the evolution. And the preliminary result is here. So again, we look at the bare quark momentum broadening and also the momentum p perp square evolution for the total. And if you look at the probability plot, so the total is always 1. what is plotted in addition to the previous one is that we also plot the probability of the initial quark state. So it will start with 1, but it's a decrease. So this indicates the gluon radiation and also interaction with the background field that would take the initial state to the higher excited just quark states. Okay, so to summarize, so with this work, we demonstrated a non-perturbative method to investigate time evolution problems with lifelong Hamiltonian formalism. So we studied the quark nuclear scattering in the quark plus quark gluon space. Okay, I'm almost finished. And then we analyzed the individual and combined effects from the different part of the Hamiltonian kinetic energy term gluon emission, the interaction with background field. A major advantage is that one can smoothly vary the relative magnitude of the above 3 effects. And so this would allow us to go to different physical regimes to study this problem. And then I'll also talk about the ongoing study is we'd like to understand the interplay between gluon emission and the medium interaction in momentum broadening. And also we'd like to investigate the subaconal effects by using the initial state and the eigenstate of the QCD Hamiltonian. That's all. Thank you.
Yeah, thanks for the very interesting talk. I had 2 questions.
Yes.
So normally people model a medium with some fluctuating background field, and then
Yes.
they evaluate the correlator, and it is just at equal times. But now you have a background field.
Yes.
This approach of only using a correlator, would it be inconsistent for CGC?
Not inconsistent. So if you're talking about like a calculation with the correlator, so that's on the probability level. And so the evolution what we are doing is on the amplitude level. So on the amplitude level, so the triangular bracket, so that is indicated as the configuration average. So you average over rho. So that's how you average over those fluctuation of different configuration. So that is done at the observable level. So like when you calculate cross section or the people square, and then what you average over different configuration.
Right, but if I already have a calculation of say Q hat in CGC, and then I use sort of the more traditional approach of just calculating the cross section directly, is that still consistent from your point of view?
Yeah, it's the same. So that we verify in our one of the previous paper. So for the bare quark, you can calculate the cross section in the iconal limit, right? That's using the Wilson-Lai correlator. So our result agree with that. We verified that before.
Okay.
Yes.
And is there probability of having, say, 2 gluon emission, or is that heavily suppressed?
That would be next to consider. So in order to have a 2 gluon, okay. So to frame this differently, so throughout this evolution, there are actually multiple gluon emission, but we could only have and max 1 gluon at each x plus time. So it's like a different kind of approximation as one compared to what one do perturbatively order by order.
Okay, maybe a final question. So, sorry, there have been 2 groups evaluating Q hat in CGC. Alina will talk about one work, and then there's a group in Vienna. Do you know whether your Q hat compares, the size of it compares with those earlier works?
Oh, okay. I think I should do that later. Yes. Thank you.
Well, thank you. This is really, really interesting, Alice's perspective for, in particular, this coherence demonstrated beautifully. I just have one question. At the end, you talk about the PT broadening of the quark and glue state. So in that case, how do you define the Q hat? I mean, one broadening for this state is that the PT broadening for Q and glue sum together, or how do you define it?
Oh yeah, so this is also my question actually. So we are also trying to understand how should we interpret there. So what we calculate here, like people sphere, is the total. So though we start with the initial state, it's go to higher state. But when we do the people sphere calculation, we consider the whole state. But I think to look at like a momentum broadening, if you think about the gluon emission, you should let some gluon that go outside of the state, right?
Yeah.
Outside the state. So that's also what we are trying to interpret here. So here we use the ground state as the initial state, but for the excited quark gluon state, the draft quark state, one could characterize it, classify it into two categories. So one is that the draft quark state have higher central mass momentum, but it could also have a larger relative momentum. So we are thinking about maybe the going from ground state to higher relative momentum would.
Yeah, I think, I mean, if the quark and gluon are still in the coherent state,
yes,
the proper definition is the vector sum.
Yeah.
Here
we are using
but once you get into a decoherent state, the total probably is the square of 2. You know,
so when we calculate this,
so there must be some kind of transition the Q hat, I mean the total momentum.
Yes.
When you transit from coherent to incoherent state.
Mm-hmm.
Maybe it's a good look at it.
Yeah. So when we do the vector sum when calculating the people square of the total system. Okay.
Other questions? Okay, so let's thank the speaker again.